Okay, so this tutorial is going to be on conducting correlation and regression analyses in SPSS. The data that we have comes from the textbook chapter. They have yet another silly example involving zombies. I don't know what's up with these guys. They really like the zombies. So just to be consistent with the textbook, I'm going to just go over the same data. And I think the consistency will be helpful. So um, really, correlation and regression are statistical analyses that are used to test associations between two variables that are, in the SPSS language, score variables. And so when variables are measured using a quantitative scale, it could be an equal interval scale, it could be a ratio scale. It is often desirable to see if there's a relationship or an association between those two variables. So a correlation tells us that, and then we can use a regression procedure, which is very related to correlation, but regression allows us to predict scores on one variable when we know values on a second variable. So we can predict values on a criterion if we know values on a predictor variable. So our sample data here, we have 12 zombies, and these zombies are students in a stats class. And so they actually did the thing that I often have been complaining about, but they finally did it, which is to basically have a participant variable. So we have a unique identifier for each of our participants. So that's a good best practice. The second variable is eaten. So this is the number of classmates that were eaten. And then this third variable is a score on a statistics exam out of 50. So in our variable view, all of our variables are numeric. We've got scale variables for eaten and exam. Notice that these are ratio variables, if you remember scales of measurement from stats class, because it's possible to have a true and meaningful zero on both of those. So, and then I've labeled both of the variables as well. So there we go. All right. So for our first procedure, what we're going to do is run a correlation. And so you might remember from stats class, if you've gotten here, if you haven't gotten here, I'll just tell you a little bit about a correlation. So a correlation is a measure of association between two score variables. A correlation can range between 1 and -1. And these values basically tell us the amount of change that we can expect in one variable based on change in a second variable, specifically in standard deviation. So it tells us more specifically the amount of change in standard deviation units in one variable that is associated with change in a second. So again, that can range from 1 to -1, and the closer a correlation is to 0, the weaker the relationship. So two variables would be not associated at all if there's a 0 correlation, and they'll be more directly related the closer that value gets to either 1 or -1. 1 being a perfect positive correlation where high values on one variable are paired with high values on another, low values paired with low. Alternatively, a -1 means a perfect inverse relationship, such that the highest score on one variable is associated with the lowest score on the other, the lowest score on one variable associated with the highest score on the other. And that's about all there is to it. Now, correlation is both a descriptive as well as an inferential statistic. So by descriptive, we can purely use the correlation to describe the association between two variables, but often what we're interested in doing is deciding whether there is an association between two variables in a population. So we'll use a sample of scores where we have two different scores on two different variables. Okay, so two scores for each person. And we're going to use that sample as a way to test whether there is an association between these variables in the population. So there is a test of statistical significance to determine whether that correlation is something real and true and meaningful, or whether it is just due to randomness or sampling error. The idea that we have these 12 zombies, but this sample of 12 zombies, if we do in fact find a correlation between eating classmates and the exam, it could be due nothing more than just to pure randomness. And so we have a statistical test to say, hey, is that correlation large enough that it would rule out the possibility of being random? All right, so that's the conceptual background. And then as you'll see, it's fairly easy and straightforward to run this analysis in SPSS. So we're going to go to our Analyze menu. Okay, and from our drop down, you'll see that there's a correlate menu. Now we have several different types of correlations. What we're going to select is bivariate, bi meaning two, because we have two variables and we just want the association between these two variates. So we want a bivariate correlation. It's our first choice. Okay, so in our dialog box, we've got our field here, and we're just going to move over the variables that we want to analyze. So we don't want to move over zombie, our participant variable. I've seen that from students, and that students are moving over that participant variable, and it doesn't make any sense. All right, so there's our two scale variables of interest. Now you'll notice that there's a lot of options. For our correlation coefficient, we're running a Pearson correlation. There are other types of correlations, some of which you may have learned in stats class, some not. For instance, a Spearman correlation is appropriate when we have data that is ranked. But just go ahead and leave the default. We're running a Pearson correlation named after Carl Pearson, the person that came up with the statistic. You'll also see that there's, on our test of significance, we've got a choice between a two-tailed and a one-tailed test. You might actually remember this from doing t-tests in stats class. Interestingly enough, or z-test for that matter, interestingly enough, you don't get the two-tail or one-tail option when running t-tests in SPSS. This is kind of the first place that this shows up, which I think is actually unfortunate. But this coincides to having either a directional or a non-directional hypothesis about the correlation. So for instance, a researcher might predict ahead of time that they believe that there will be a positive association between two variables. Alternatively, that they might predict that there will be a negative association between two variables. That's a directional hypothesis, and in which case you would test the statistical significance of that directional hypothesis using a one-tailed test. By default, we'll just leave a two-tailed test. This is when there's no particular direction of the effect predicted. That is, the researcher says, well, I just think that the two variables will be associated. I don't necessarily know whether they will be positively associated or negatively associated, so I will do a two-tailed test of significance. There's the option to flag or not flag significant correlations. The default is to have that flagged. That's how I would leave it. In options, what you can ask for is means and standard deviations of your two variables. You can include this if you want. I will. I think it's a good thing to include, but you don't have to. Okay, so I'll continue. Style and bootstrap, don't worry about. And then you'll see this last thing to either show only the lower triangle and then the option to show the diagonal or not. Okay, the default is not to select those, and I'll show you what the output spits out, and then we'll go back and we'll select those options just to give you a sense of what that means. Okay, so you should paste it for your lab assignment, but I'm just going to go ahead and click OK. All right, so here I ran descriptive statistics. Again, you don't necessarily need to do this for your lab assignment, but you can if you want. And so this just tells us that the average number of classmates eaten was 6, and the average score on the exam was 37, and we can see that there's some amount of variability, which we knew that. We could see that not everybody was at the mean on both. So here's our correlation matrix. Okay, so what we have are 2 rows and 2 columns, and there is redundant information in this correlation matrix. So the first thing that we see is actually in the first row we've got the number of classmates eaten, and then in the first column we've got the number of classmates eaten. So that we can see here that the Pearson correlation is 1. That is, any variable correlates with itself perfectly. So it doesn't provide any useful information, but it is there, right? The correlation of a variable with itself is 1. What we're more interested in, of course, is the correlation between number of classmates eaten and score on the exam. And so we have that information in 2 places. We've got it in an upper what's called kind of this upper part of the matrix and the lower part of the matrix above the diagonal. Okay, so this is known as the diagonal, where we've got the correlations of the two variables with themselves, and so we'll have both the correlation above and below that diagonal. So here's what we're looking for. We see that the value of the correlation is 0.983. So we can see just based on the magnitude of that correlation, recall that the highest a correlation can be is 1, either positive 1 or negative 1. So we're very, very close to that perfect positive correlation. So there is a very strong correlation between the number of classmates eaten and score on the exam. And because we have a positive correlation, we can interpret that as meaning that the more classmates eaten, the higher the score on the exam, or the fewer the classmates eaten, the lower the score on the exam. So basically, high scores are paired with high scores, low scores are paired with low scores, and middles are paired with middles. That's a positive correlation. This correlation is statistically significant, so that's our 0.000, our two-tailed significance level. Similar interpretation as we've been having with our previous tests of significance. What this is telling us is that this correlation is not due to randomness or sampling error. This correlation is, the literal interpretation is that this correlation is improbable. You wouldn't get a correlation this high if there was, under the null hypothesis, if there was no true association between these variables in the population. Now, we don't know exactly what that true correlation is in the population, but we can be very confident that it is a positive correlation because our sample correlation is positive. And our best guess is that that correlation is probably somewhere in the, in this range, but we can't be certain, right? So we know that there's a positive correlation, and because of the inference that it would be very, very unlikely, some probability level less than 0.001, that we would get a correlation this high if those two variables weren't associated at all. So that's our significance level. Okay, our significance level is not 0.000, meaning zero probability. It's just SPSS cut off the number, so it's something very low. So we can say that the probability of getting a correlation this strong, assuming that there's no true correlation between these variables in the population, is something less than 0.001. All right, so that's the interpretation on that. Let's just go back. Let's go back to analyze, correlate, bivariate. And I just wanted to now include the option to show only the lower triangle. And I'll still show the diagonal and click OK. And so what you can see is that just removes kind of the redundant piece of information, right? We don't need both. There's the redundancy. And actually, if I guess I need to keep doing that. Let's just go back and let's just wipe out the diagonal now. There we go. And then here we just completely wiped out the diagonal. So it is completely your choice in terms of what output you like to look at. If you can, you just get additional information, you get redundant information that you don't need. Any way you do it is fine. Okay. But again, we can say that there is a strong positive relationship between these two variables. The interpretation would be that the more classmates eaten, the higher the score, and the fewer the classmates eaten, the lower the score, and that is a statistically significant relationship, meaning that we can be confident based on this sample result that there is some positive relationship in the population, not just among these 12 zombies, but in the population, among all zombies. All right. So the next thing that we're going to do is a regression analysis. So this is, you could call it a close cousin of correlation. It is very much based on the association between two variables. But with regression, we conceptualize one of our variables as a predictor and one as an outcome. And so the applied purpose is to try to predict scores on one variable from known values on another variable, the predictor. and that prediction equation takes the form of a straight line. All right, so we've got our regression menu, and you'll see that there's tons of choices in the regression menu. So regression ends up being can be a very advanced procedure. We are going to learn the most simple, most basic version of it's actually called simple linear regression. So simple linear regression is just the case of having two variables, one which is a predictor and one is an outcome. All right. So we're going to use the linear command under regression. So linear. All right. So again, here you're going to see that we've got a choice for a dependent and an independent. So our dependent variable is the outcome variable. The independent variable is the predictor variable. So you have to choose one or the other, and it's really based, as a researcher, it's based on what is your applied question of interest. When you're doing your lab assignment, it is going to be your job to take a look at the question and say which one of the variables is being conceptualized as the outcome and which is being conceptualized as the predictor. The outcome is your dependent variable, the predictor is your independent variable. In this particular example in the textbook, the outcome was score on the stats exam, and the predictor was the number of classmates eaten. Okay, so I'm moving score on the stats exam to dependent and number of classmates eaten as the independent variable. The idea is that if we know how many classmates a zombie has eaten, that will allow us to predict how well they do on the stats exam. So hopefully nobody's sensibilities are being like offended by this. I just think it's a very silly thing, but all right. Now you'll see tons of options. Okay, again, regression is actually a very powerful tool. We're going to keep it very basic. So you'll see there's this block 1 of 1, the next, method, enter. You can safely ignore all that for the purposes of running a simple regression. Okay, in our statistics, again, all kinds of things that you can request. If anything, we know about descriptive statistics, so you can select that, but you really shouldn't select anything else because it's going to muddy up your output. It's just going to produce a lot of numbers that you haven't learned yet and won't be interpretable. So other than descriptives, which you don't even need to do, I'll leave it off for the time being. You really don't need to do anything with your statistics, so you can leave that alone. Here's your plots. Now, the lab assignment is going to have you do a scatter plot. Unfortunately, we can't easily create a scatter plot in this regression menu. We have to go to the graphs menu. You'll see all these choices and you're saying to yourself, what is this? Z-pred, what is this? SR-red. These are used for diagnostics to determine whether the assumptions of regression have been violated or not. So we're not going to mess with it. This is stuff that you learn in an advanced stats class. But what I want to tell you about this is that we can't run the scatter plot that we need using our regression dialog box here. Okay, so it'd be very tempting to try to get your scatter plot, but you can't get it from there. Save option, we're not going to mess with. Options menu, style, bootstrap, we're really not going to mess with any of this. Okay, it's a very straightforward analysis. If anything, you can get descriptives, but otherwise, all you need to do is specify your dependent, your independent, and then paste it to save it. And I'm just going to go to OK. All right, now here you get more output than I could say that you need for the lab assignment, or in terms of what I'm asking you to interpret. You will potentially learn about this in your stats class, but for the sake of this lab assignment, the table that you really need to focus on is the last table in the output. Okay, so you'll see the first thing that I'll just go through it so you see what it is. The first thing that you get is just a statement of what variables were entered in terms of what is the independent variable and what is the dependent variable. The second table provides values for r squared, and then adjusted r squared. These are measures of effect size, which you may or may not learn about in stats class. Essentially what your R squared tells you is the amount of variability in your outcome variable that is explained by scores on your predictor variable. So what this R squared value of 0.965 is telling us is that 96.5% of the reason that exam scores are different from average or from the mean can be attributed to the number of classmates eaten. So the reason why what we're able to explain, right, because not everybody has the same score on the exam. I believe that the mean on the exam was 37. There's people that scored higher, there was people that scored lower, there was people that scored at about 37. Why do some people score higher and some people score lower? We're able to explain that, or we're able to account for that difference by knowing something about how many classmates were eaten. We know because there is a positive correlation, and a very strong one, in fact, we see it here with the R of 0.983, that we know that the more classmates eaten, the higher people scored, and the fewer classmates eaten, the lower people scored. And so we're actually able to define just how much of that variability in exam scores we can account for by knowing something about how many classmates were eaten. And in this case, we can explain 96.5% of that variability in exam scores. So almost all of it. So that's a huge number, and frankly, that's actually unheard of in social and behavioral sciences. But statisticians have come up with guidelines or benchmarks for interpreting the R square, which is our measure of effect size. So typically, if we can explain about 12%, that's a huge effect. So this is like a huge, huge effect that you never actually get. But these are made up data. All right, this is an analysis of variance table. This tells us overall that our regression equation is statistically significant. And that's about all I'm going to say about that. Essentially, it just means that our regression equation is doing a better job of explaining variability in exam scores than if we were to use the mean is our guess for everybody. Okay, which is a very bad model, but that's our baseline point. So if you take stats with me, we get really deep into that, but I'll leave it at that for now. So what I really want you to focus on is this final table. What you see here is we've got two values. We've got a value for our regression constant, and then we've got a value for number of classmates eaten. So our this is actually our slope. So this first number, 29.449, is our regression constant. This is our exam score, our predicted exam score when the number of classmates eaten is 0. Okay? So in our regression equation, our straight line equation, you might have also learned the regression constant as the y-intercept. So it's where our regression line intersects the y-axis. So this is telling us is that all the way kind of on the left side of the two-dimensional space where we would graph the line in the dots, which we'll pull up that scatter plot in just a little bit. 29.449 is where our line intersects the y-axis. But I think the best, most interpretable interpretation of this value is it's the predicted exam score when the number of zombies eaten is 0. Okay, so when our predictor variable is 0, it's the predicted value of y. There is a test of statistical significance for this regression constant. In most applications, it is kind of a meaningless test. Essentially, this test is a test of whether the value of the regression constant is different from 0. And we see a very huge t-statistic and a statistical significance level. So what we can say is that, yes, 29.49 is statistically different than 0, but it's often not a very meaningful test. The more meaningful statistical test, anyway, would be a test of the regression coefficient, often called the slope. Okay. So this number, our regression coefficient, is 1.258. In general terms, this is the predicted change in y for every 1 unit increase in x. In the context of our problem, what this tells us is that we predict an increase of 1.258 points on the stats exam for every one additional classmate eaten. Okay, our predictor value is our predictor variable is classmates eaten. So for one additional classmate eaten, we predict that a zombie will score 1.258 points higher on the exam. All right. Now this is the unstandardized coefficient. So this is in the original metric. Okay, our original metric was however the stats exam was scored and zombies eaten. We can also standardize this number, okay, which you'll notice is the exact same as the correlation coefficient. So essentially what we have here is if we are to convert number of classmates eaten into a z-score and our exam score into a z-score, and then we use the same regression equation with our z-scores, our regression coefficient, otherwise known as the slope, is exactly equal to the correlation coefficient of 0.98. Okay, so that's kind of a neat fact, is that our standardized regression coefficient is exactly equal to the Pearson correlation coefficient anytime we do a simple regression, anytime there's just two variables. The standardized regression coefficient will be exactly equal to the correlation coefficient. It is often the case, most interpretable, however, to use the unstandardized coefficient, because that way we can talk about the original metrics and we can make conclusions along the lines of, for each additional classmate eaten, we expect the zombie score to increase by 1.25 points on the exam. Okay. In standardized units, we would have to say, for every one standard deviation increase in classmates eaten, we predict exam scores to go up by 0.98 standard deviations. So it's not as straightforward of an interpretation, and for that reason, it's the unstandardized coefficient is used for interpretation purposes. And we can see that that is a statistically significant relationship that we already knew from the correlation coefficient, which is just to say that that is not due to chance or randomness or error. That is based on some real relationship between those two variables in the population. All right, last thing that we're going to do is we're going to get a scatter plot. So here we have to go to our graphs menu. So graphs and then legacy dialog. So we did graphs much earlier in the course, so we have to jog our memory again. It's in a very non-intuitive place, but we go to graphs, legacy dialogs, and then we're going to go to scatter. So we're going to create a scatter plot of this relationship. From here, we're just going to select a simple scatter plot and then click define. All right. So by convention, our dependent variable, which is score on the stats exam, is plotted on the y-axis. So that's our vertical axis. Okay, so you should have your dependent variable on your y-axis, and you should have your independent variable on the x-axis being the horizontal axis. You should put a title. I'm going to be very lazy and not put a title. You should also paste that. I'm just going to go ahead and click OK. So here's our scatter plot, and so this is a great visualization of the relationship between number of classmates eaten and score on the stats exam. So each of these points is, you'll see that there should be 12 points here. So each one of these dots represents one of our 12 zombies, and we could go back to our raw data and actually see, okay, this is the zombie. Well, why don't we do that real quick? Okay, this zombie number 12 ate 14 classmates and had an exam score of 47. And so that's that person right there. So you can, we've got each of our zombies plotted in this kind of two-dimensional space, predictor on the x-axis and dependent variable or outcome on the y-axis. what we're going to do is we're going to add the line of best fit. Okay, so this would be our regression equation that is defined by our regression constant and our regression coefficient. Ultimately, the prediction equation takes the form of a straight line, and so what we can do is we can visualize that straight line equation as the line of best fit passing through these dots. The way to produce that is to double click on your graph, and then you want to go up to your menu up top here and go to the Elements menu. There's a way to produce it using one of these icons here, but they're so small and I'm getting old and my eyes are failing me. So it's a lot easier just to go to your Elements menu right up top here. And then you want to go to Fit Line at Total. All right, so Elements menu, Fit Line at Total, select Fit Line at Total. And then by default, it brings up the linear fit method. That's what you want to select. And that is it. That is all you need to do. There's many other options here, but for our purposes to produce the regression equation, and it makes sense because that's mostly what people are interested in, that's the default options for SPSS. Okay. Apparently that just does it automatically. We don't need to apply it. So I'm going to close and close. And then what we'll see is we've got that that line of best fit and the regression equation, which is basically plotted through our data. So you'll see that our regression equation takes this form of a straight line where our predicted y, okay, our predicted exam score is a function of the regression constant, which was 29.499 or 29.45, okay, plus our regression coefficient, 1.258, so we just got 1.26 here, times x. So what this allows us to do is we can now substitute in values of x, and that will give us a predicted value of y. So if we say, like, all right, well, if somebody eats 5 classmates, what would we predict their exam score to be? Okay, and that number, we'll find it, that is the exact, the regression line will pass through that value. Okay, similar thing. Okay, if somebody eats 10 classmates, what is our predicted exam score? So in practice, regression is used to come up with a prediction equation using a sample of data that is often then used for kind of future applications. So you can have a sample of people. Maybe you want to know what the relationship is between select scores on the SAT and success in college. And if you do that study, you might learn that there's some relationship between SAT scores and first year GPA. And so that could be used then for establishing different, say, cutoffs and admissions criteria and things like that. Okay, I believe that that's it. So for your lab assignment, you're going to produce a correlation. You're going to produce a regression analysis. You'll be responsible for interpreting the numbers, and then you'll be responsible for producing a scatter plot with a line of best fit. So, and as before, it's slightly different data. It's related, but don't use the data from this tutorial. Use the data from the textbook. Hope you found that helpful. Good luck with your lab assignment this week.